Good morning. Today I am going to solve problems about optimization in heat transfer in double pipe heat exchanger and shell and tube heat exchanger. First, the problem for the double pipe heat exchanger goes this way. A condenser for a distillation unit must be designed to condense 2,268 kilograms per hour of vapor. The effective condensation temperature for the vapor is 350 Kelvin. The heat of condensation for the vapor is 4.65 times 10 raised to 5 joules per kilogram. Cooling water is available at 294 Kelvin. The cost of cooling water is $25.60 per 1,000 cubic meter. The optimum HTC or the heat transfer coefficient is 284 watts per square meter Kelvin. The cost of the installed heat exchanger is $366 per square meter, and the annual fixed charges including maintenance are 20% of the initial investment. The heat capacity of water is 4.2 kilojoules per kilogram Kelvin. If the condenser is to operate 6,000 hours per year, determine the cooling water flow rate in kilograms per hour for optimum economic conditions. Before solving the problem, we have to be familiar with the variables. So T prime is the exiting temperature in degrees Celsius. Q is the heat from condensing vapor. U is the overall heat transfer coefficient in watts per square meter Kelvin. A is the heat transfer area in square meter. K sub F is the annual fixed cost per initial cost of installed equipment. T sub 2 is the exit temperature in degrees Celsius. W is the mass rate in kilograms per hour. CW is the cost of cooling water per kilogram. CP is the heat. C sub P is the heat capacity of water in kilojoules per kilogram. T sub 1 is the entering temperature in degrees Celsius. C sub A is the cost of installed exchanger per square meter area. Delta T sub M is the log mean temperature drop based on counter current flow, and H sub 1 is in hours per year. So for solving this problem, we have to use the equation for the counter current flow, which is this. T prime minus T sub 1 over T prime minus the T sub 2 optimized or the exiting temperature minus 1 plus ln of T prime minus the T sub 2 optimized over T prime minus T sub 1 is equal to 3.6 U 8 times H sub Y times CW over K sub F times C sub P times C sub A. And for the assigning of variables, we have T prime or the temperature of the steam is at 350 Kelvin. The heat capacity is at 4.2 kilojoules per kilogram Kelvin. T sub 1 or the entering temperature is at 294 Kelvin. C sub A is $366 per square meter. U is in 284 watts per square meter Kelvin. K sub F is equal to 2. H sub Y is 6,000 hours per year. The L sub steam or the heat of condensation of vapor is at 4.65 times 10 raised to 5 joules per kilogram. CW is at 25.6, and the flow rate of the steam is at 2,268 kilograms per hour. Next, substituting the values into the equation, we would come up with this equation. So 350 minus 294 over 350 minus T2 op minus 1 plus ln of 350 minus T2 op over 350 minus 294, which is equal to 284 times 6,000 times 25.6 over 1,000 times 3.6 all over to 2 times 366 times 4.2 times 1,000. Then our optimized exiting temperature or T2 op is equal to 326.435 Kelvin. So by getting the optimized exiting temperature, we can now solve for the mass flow rate of the cooling water by using this formula. So mass flow rate of the cooling water is equal to the flow rate of the steam times the heat of condensation of steam over Cp times 1000 over the optimized exiting temperature minus T sub 1. Then substituting the values, 2,268 times 4.65 times 10 raised to 5 over 4.2 times 1,000 times quantity 326.35 minus 294. So the mass flow rate of the cooling water is 7,741.701 kilograms per hour. And that's the optimization in heat transfer for a double pipe condenser. So for the problem on optimization in heat transfer for a shell and tube heat exchanger, the problem goes like this. An air cooler consisting of a bundle of 118 BWG copper tubes enclosed in a well-baffled shell is being built to cool 45,000 pound mass per hour of air from 200 degrees Fahrenheit to 120 degrees Fahrenheit. The air flows under pressure through the tubes of a one-shell, two-tube pass heat exchanger. Cooling water at 80 degrees Fahrenheit is under sufficient pressure to force it through at any desired rate, flows through the shell. The overall heat transfer coefficient based on the inside fluid is 7.8 BTU per hour square foot per degrees Fahrenheit. Cooling water costs $20 per 1,000 cubic foot, and the annual fixed charges on the cooler are $50 per square foot per year. Calculate the optimum exit temperature of cooling water and the optimum length of tubes. For the familiarization of the variables in the optimization of heat exchanger in a shell and tube, T sub 1 prime is the entering temperature of the process fluid in degrees Fahrenheit. T sub 2 prime is the exit temperature of the process fluid in degrees Fahrenheit. W sub U is the mass rate in pounds per hour. C sub U is the cost of utility fluid per pound. CPU is the heat capacity of cooling water in BTU per degrees Fahrenheit per pound. T sub 1 is the entering temperature in degrees Fahrenheit of the utility fluid. T sub 2 is the exit temperature of the utility fluid in degrees Fahrenheit. Q is the heat transfer in BTU per hour. H sub Y is in hours per year. F sub T is the correction factor. U sub O is the overall heat transfer coefficient. A sub O is the heat transfer area in square feet. K sub F is the annual fixed cost per initial cost of installed equipment. And CAO is the cost of installed exchanger per square foot. The equation that we need to use in solving the problem about optimization in shell and tube heat exchanger is this. So, quantity squared of 1 plus T1 prime minus T2 prime over delta T sub 1 minus delta T sub 2 times ln of delta T sub 2 over delta T sub 1 minus 1 plus delta T sub 1 over delta T sub 2, which is equal to the correction factor Ft times U sub O times H sub Y times C sub U over CPU times Kf times CAO. And assigning the values for the variables, we have the entering temperature of the process fluid is at 200 degrees Fahrenheit. The exit temperature of the process fluid is at 120 degrees Fahrenheit. The entering temperature of the cooling water is at 80 degrees Fahrenheit. U sub I is equal to 7.8 BTU per hour per square foot per degrees Fahrenheit. D sub O is equal to 1. D sub I is equal to 0.9. H sub Y is equal to 8,760 hours per year. U sub O, which is calculated by U sub I times D sub I over D sub O, is equal to 7.02. Kf times CAO is equal to 50. C sub U is equal to 20 divided by 1,000 times 1 over 62.4. and CPU is equal to 1. So in this problem of optimization, we are using iteration. We assume values of ft so to solve for delta t sub 2, and by using delta t sub 2 we can solve now for the exit temperature of the cooling water. But first, to know if the value for ft is correct, we will solve for the value of r and s, and by using the graph to get the ft so that we can know if the value that we assume for ft is correct. So plugging in the values into the equation, we have this. So assuming ft is equal to 1, the solution is 1 plus 200 minus 120 over 40 minus delta t sub 2 quantity squared times ln of delta t sub 2 over 40 minus 1 plus 40 over delta t sub 2, which is equal to 1 times 7.02 times 8,760 times 0.000320513 over 50 times 1. Then delta t sub 2 is equal to 68.66. By using delta t sub 2, we can find or we can solve for the exit temperature of the cooling water, wherein delta t sub 2 is equal to the entering temperature of the process fluid minus the delta T sub 2 that we find or that we solve by using the equation, and the exit temperature of the cooling water is 131.34. To check if the FT or the value that we assume for FT is correct, we have to solve for R and S. So we will use this formula. So to check the FT, R is equal to T sub 1, or the entering temperature of the cooling water, minus T sub 2, or the exit temperature of the cooling water, divided by T sub 2P, or the exit temperature of the process fluid, minus T sub 1P, or the entering temperature of the process fluid. R is equal to 0.642. Then S is equal to T sub 2P minus T sub 1P over quantity T sub 1 minus T sub 1P. Then we get 0.667. And by using the graph to find FT, we will use this kind of graph. So the value of f sub t that I get from the graph is 0.62, which is not equal, or which is not near enough from the assigned or from the assumed value of ft, which is equal to 1. So we have to iterate again, or to assume, but we can use 0.62 for our next iteration. And after some other time after many times of iteration, we assume that f sub t is equal to 0.74. Then plugging in the values again into the equation, we can get, or we will have delta t sub 2, which is equal to 73.63. Then by using delta t sub 2, we can get the exiting temperature of the cooling water, which is 126.37. And by doing the same procedure, getting the R and S, and by using the graph, we check the value if if f sub t, or the assumed value of f sub t, would be equal or would be near to the value of the ft that we can get to the graph by using R and S. So by using the values of R and S, which are 0.58 and 0.667, and plugging into the graph, the value of ft that we get is 0.73, which is near or equal to 0.74. So since it is near enough, we can use now the T sub 2, or the exit temperature of the cooling water to solve for the length. So, by using this equation, Q is equal to U sub O times pi times the outside diameter of the tube times the length times del T sub M, which is equal to W times T sub P times T sub 1P minus T sub 2P, where the mass rate is equal to 45,000 and the heat capacity is 0.24. Then plugging in equations, the length of the tubes that we find is 8,529.75 feet.